Okay, so thanks for this opportunity. So I'm going to talk about some kind of estimation of the time-varying parameters of the models by the data assimilation. So this slide shows the problem setting for most of us. So we have the physical dynamic model to update the state variables, but we have the observation data, which is nearly independent information to the modeling system. So the DA try to integrate them to get the best estimate of the state variables. But as most of you may know, that this framework substantially suffers from the misspecification of model parameters, or even the misspecification of the model physics or the equation selection, so which is called a systematic model error. So how to resolve the systematic model error within the framework of DA is super important, I think. And hold on. Okay, so today I would like to suggest some kind of bit new direction, which is called the special temporary distributed parameters. So in the most model, the parameter is the fixed variable. This is actually the definition of the parameters. So your parameter space is just a point, and using that point, you can drive the dynamic model. And the data assimilation try to integrate your observation into that state space. But if you assume the special temporary distributed parameters, the parameters are no longer fixed variable. So it can be the spatially distributed, and also the parameters can change in time because of some unknown or unresolved dynamics. So our current task is to estimate that special temporary distributed parameter from the observation. And then by analyzing that, the special temporary distributed parameter, we can understand, or we can discover some unknown physics or unknown or unresolved dynamics in the from the original model. And this is actually practically difficult problem. So simultaneous update of the state and the parameters can be done by using some sequential filters, such as ensemble Kalman filter and the particle filter. So this is a classical study in the hydrology. So in the hydrology, successfully adjust the both state and the parameters by using a sequential filter, but it is still practically difficult, especially when your parameter is a time varying, or you have a large number of the parameters. And in most cases, the tuning of the inflation factor is a key. So if you would like to track the rapid change of the true model parameter, you need to inflate the prior covariance of the parameters. But yeah, you know, if you inflate it too much, you're going to destroy the system or the model. But it is more important than the state estimation, because you don't have you have no information about the dynamics of the parameter a priori. So it is quite important to get the appropriate inflation to track the true dynamics of the model parameters. So to solve this issue, we are now proposing some new algorithm, which is called a hybrid offline and online parameter estimation, or HOPE. And so HOPE has two steps. So first step is called the offline batch optimization. So in this step one, we still assume the parameter is a fixed variable. And we're going to try to estimate the posterior distribution of that fixed parameter, which is shown in the gray in the right figure. And we would like to get this posterior distribution by comparing the long-term climatology of the model and observation, which is not dependent to the initial conditions. And then we're going to estimate the spatial temporary distributed parameters by using the online data assimilation, which is the step 2. So the parameters are sequentially estimated. But in this step, we're going to incorporate the results of the offline batch optimization showing gray distribution to stabilize the filter. So that's the fundamental idea. And I have two implementations of the HOPE. First one is the ensemble Kalman filter, and another one is the particle filter. So I'm going to start from the ensemble Kalman filter version of the HOPE. So as I said, we're going to start from the offline batch optimization to get the climatologically correct parameters. So first, we're going to define our targeted climatological variables. So maybe it might be in the atmospheric science, it's going to be kind of spatial distribution of the long-term average of the precipitation, temperature, or pressure field, or and so on. And then you're going to perform the ensemble simulation with any combination of model parameters, theta, in parallel. And then this is a trick. So you're going to learn that data set to construct a surrogate model by machine learning. So in this study, we used the Gaussian process regression. So the point is that this machine learning approximates the response surface between the parameters and your targeted climatological variables. So in this model, you just put the parameters and get the climatological variables without integrating the real physical model, so which can accelerate the optimization process. And then you can get the posterior distribution by any kinds of method. In this study, we used a Markov chain Monte Carlo. So the point is the parameters are evaluated by the surrogate model, not by the real physical model, so that we can use the computationally intense optimization method. And because we would like to use the ensemble common filter, so we're going to approximate that posterior distribution as a Gaussian distribution to get the mean with the sample mean and the variance. All right. So although it is quite costly, but I believe that using a surrogate model, we can perform these kinds of offline batch optimization even in a quite complex model such as the atmospheric model. And actually, some of the previous works try to do it in the intermediate resolution atmospheric model. And then the next question is how to incorporate this gray climatological distribution in a framework, in the ensemble common filter framework. So our base algorithm is the LETKF, but it can be applied to any ENKFs because we're going to start just from the cost function. So this is the cost function to be minimized, and this is the background term. So because we would like to adjust both state x and the parameter theta, so it's a bit different from what you saw in the textbook, but this is the background term. And this is the observation term. And what we do is just to add a new term as a parameter regularization term. So it is quite natural, right? Because the background term can be recognized as a regularization to the model in the machine learning viewpoint. So in that, we would like to regularize our estimation to the climatologically correct parameters, fixed parameters. And then the real kind of implementation, we found the two different flavors to minimize this cost function. First one is that we're going to integrate this parameter regularization term into the observation term to get this cost function. And this cost function implies that what we should do is just to assimilate the climatological parameters into the system. So this method is called the pseudo observation approach. And another flavor is that we're going to integrate this regularization term into the background term. This is called a regression to climatology. I don't have enough time to explain the details about it, but first we're going to adjust our parameter ensemble into the climatologically correct distribution, and then we're going to assimilate the real observation into the system, right? And we apply this whole ENKF into to the two-scale Lorentz 96 model. So we have a large and slow scale 9 grids, and we have a small and fast scale. This is actually 20 grids. So 20 grids, and we have some subgrid scale impact from small scale to the large scale. So that's the kind of nature run. But we assume that our prediction model has just a large scale. And also the subgrid scale impact from small scale to large scale is parameterized as a fixed model parameter, FK. So our task is to estimate this FK as a special temporary distributed parameters. And first, we perform the offline batch optimization using the autocorrelation of the systems. So we're going to compare the simulated and observed autocorrelation to get this posterior distribution. Okay. So, and this slide illustrates what I want to do here. So in the true world, we have a small scale dynamics. This is the Hochmüller diagram. And then we have some subgrid contribution, which has a wave structure. And then we got this, the large or main scale time series. But in my original model, we don't know anything about the small scale here. Therefore, I hypothetically parameterize the subgrid scale impact as a fixed parameter. So that your kind of estimated main scale doesn't have any strong wave structure here. But if we can successfully estimate a special temporary distributed parameter, we can recover, we can reconstruct this wave structure of the subgrid scale from the sparsely distributed observation in the large scale. So that is what I want to do. And this slide shows the performances of the HOPE ENKF. So the horizontal axis shows a multiplicative inflation factor for the states, and the vertical axis is the multiplicative inflation factor for the parameters. And the top row shows the original LETKF. We call it the no hope experiment, and it has no hope to solve this problem. But if you integrate the climatologically correct the distribution of the fixed parameter in the hope ENKF, you can get a good result. So hope ENKF is much better than the original LETKF. And also the good news is the performance is less sensitive to the inflation factors. In the real world application, we cannot know the true model parameter because we assume that true model parameter is driven by the unknown dynamics, right? So we cannot tune this inflation factor by looking at the model parameter estimation. So therefore, this kind of the insensitivity to the tuning inflation factor is really important, and we have some such kind of nature in our algorithm. All right, so let's move on to the particle filter version of the hope. So we have the same steps. So as I said, this is a two-steps approach. So first we need to get the posterior distribution of the fixed parameter, but we used exactly the same process. However, in the particle filter, we no longer assume the Gaussian distribution of the posterior distribution. And then this is the algorithm of the hope PF. So we first prepare this gray distribution as a fixed parameter. And then we're going to update the state and the parameters. And we weight the particle according to the distance from the observation to each particle. And then we resample it. And then we're going to keep the diversity of the particle, we often add some perturbations into the particle. That is called a mutation process or rejuvenation process. And then the differences between the original particle filter and the hope PF is here. So we're going to evaluate that perturbed particle according to the distance from that particle to the gray distribution, the climatological parameters. So if your perturbed particle is far from the climatological parameters, we're going to reject it. And then we're going to perturb the particle once again. So that's kind of iterative process. And to keep all the particles are in the right track, aligned to the gray distribution. And then we performed a real data experiment with a conceptual hydrological model. So I don't know, I think that most of you don't know very well about the hydrology, but this is a really simple but practically useful conceptual hydrological model called HIMOT. This is a simple 5-state variable and 5 parameters model. And the point is that this is a linear reservoir model. So my personal kind of research question is that can we infer the unknown nonlinear dynamics by obtaining the time-varying parameters from the observation? So although the original model is a linear reservoir model, but can we get some kind of nonlinear dynamics of the rainfall and the runoff by analyzing the time-varying parameters? That's kind of challenge for me. And then this is the top row is a time series of the river discharge.
You have 2 minutes left, Yohei.
All right, thank you. I think I have last 3 slides here. So yeah, this is the time series of the runoff, and the left one is a hope PF, and the right one is the original particle filter. So that you see that the hope PF is much better than the original particle filter. And the bottom row shows the time series of the one of the model parameters, KQ. KQ is kind of the hydraulic conductivity. So in the originally, the formulation is something like this. So runoff equals to some fixed parameter times the storage of the water within the river basins. So if you can see it, so when the flood period, when it is a flood period, they prefer to choose a higher value of this KQ. So you can see some nonlinearity. We can see some nonlinearity in when you look at the time-varying parameters. So I don't have actually the concrete conclusion about that, but I believe that we can improve or we can introduce the nonlinearity by looking at the time series of these time-varying parameters. So we are not just improve the output or state output of the physical model or state variables of the physical model, but we can contribute to construct the new equations by looking at these kinds of the time-varying, by analyzing these kind of time-varying parameters. And this is basically the shows the performances. So I think you're not so familiar with that, but this is a Kring-Gupta efficiency, KGE, for the liver discharge. So basically the whole PF is much better than the original PF, with especially when the ensemble size is small. And also you can see that the HOPE PF, the performance of HOPE PF is less sensitive to the inflation factors. So this is quite good news, right? So this is the end of my talk. So I'm now investigating the potential of the spatial temporary distributed parameters to quantify and reduce the systematic model errors within the data assimilation framework. And it is practically difficult to estimate the spatial temporary distributed parameters, so that I developed some good practical tools to efficiently estimate such kinds of parameters. And the key idea is to integrate the offline batch optimization and online sequential data assimilation. So if you are interested in, please look at this preprint or published paper. Thank you very much.
Okay, thank you for this very nice talk. I really like this approach personally. But so let's. I have a question for you. So I would guess that this approach would be especially useful with real observations when there is also unknown model error, so that the parameter estimation with standard LTKF does not work perfectly, and so you constrain it with some climatology that you have. So I was actually a little bit surprised that the regular LTKF did not work so well on the Lorentz model. Can you maybe explain a little bit more why you think this approach didn't work well in the perfect model experiments?
So actually, if you apply the adaptive inflation, it actually works. So if you change the inflation factor adaptively, it actually works. Although still the performance is a bit worse than the HOPE ENKF, but basically this is quite how to say, actually the sensitivity of the model parameters to the observation is small in this problem. So they have a huge risks to get the spurious correlation between the state and the parameters. And the original LETKF suffers from it to get the spurious correlation and get this quite an awkward parameters in some cases. But HOPE PF can prevent it because we have already have some constraints to the parameters.
Right. So if you would increase, for example, the ensemble size or something, it would perform better the regular ensemble common filter.
I believe so, but still it looks quite difficult.
Okay. Thank you.
Thank you.
So also for you, please keep the YoPad. Watch it in the next minutes to see if there's more questions popping up.
Of course. Of course.
Thank you.